Very good evening, sir. Very good morning, sir.
Good morning, Dr.
Very
Huda.
I must say a very good morning.
आपको good evening.
Now it's your
Thank,
time. Okay, sir. Welcome again, once again.
thank you.
And sir, really, I am from the background of computers. I have no idea about these mathematics, but whenever you teach all these things, my interest generates about those
Thank
things.
you. I'm so
Yes.
happy. Thank you for your positive comments.
Over to you, sir.
Thank you. Thank you. Namaste to all, and good evening, all the participants. So let me summarize. Yesterday we had a very good day of having the theoretical foundations of the quick review of probability theory, and also we started the basics of the stochastic process. We defined what is a state, what is a state space, and how to construct states within a state space, and the similarities between a set, state space, and sample space we discussed. And you all have asked very interesting questions, and I appreciate all of that. Today we are going to continue the same. As I mentioned yesterday, notation, PIJ notation, we are going to use that notation rest of the course, and whenever I change the notation I will again inform you. I will again discuss with all of you. For now we discussed, the Pij equal to probability xi xn plus 1 equal to j given xn equal to I. That's a standard notation we will follow. That means from state I to state j, the transition. So stochastic process is about the change in the value of the random variable, which is particular time. At particular time the value of the random variable transitions to the another value. The transition is the new thing which is different from the which is actually not discussed in the classical probability. So the transition things whatever we're discussing, that is the distinction between the classical probability to the stochastic process. And then we introduced yesterday in the class the notation. So let me start my lecture from there. And today I'll start with examples of the numerical examples of the matrix, the transition matrix, what we learned. Let me share my screen. So as always, stop me whenever it is not clear, or if you have any question, if you want to say any comment, feel free to stop me or raise your hand. Let me start my screen. So P, as we discussed yesterday, the symbol for transition matrix. Suppose a 2 by 2 transition matrix is given like that. 0.3 as you see on the screen, 0.3, 0.7, 0.2, 0.8. So from the structure itself, you would know that this is a stochastic process with which has two states, and the state space will have two states in that. That's what the, because it is a 2 by 2 matrix. So this is a stochastic matrix also, because if you see that the sum of the rows 0.3 plus 0.7 is 1, and 0.2 plus 0.8 is 1. So this is a stochastic matrix. Because row sums, sum of the each row is 1. Suppose say the states 0, this is 0, this is 1. So this becomes P00, this is P01, this is P10, this is P11. The elements, as you see that P00 means probability xn plus 1 equal to 0. As we discussed the notation yesterday, xn plus 1 equal to 0, given xn equal to 0. So again, I would like to highlight that this is a time. This is a time factor. This is the time again. And this is the state. And this 0.3 corresponds to this value here. 0.3. That is P00. P00. So this is the time step. One can write also x1 to x2. If n equal to 0, this is x0 to x1. Sorry. P00 stands for probability of transition changing the value of the random variable at the nth time step. So we discuss in general nth time step to n plus 1 are equal, that is same as first to second or 0 to 1, anything. That means one step, xn, nth step, xn plus 1, n plus 1th step. That's this one. Similarly, xn equal to 0, xn plus 1 equal to, that means remaining, this is a 0 to, this is 1, there is a typo here. This is 1. Sorry. This is x0, xn equal to 0. That means the value of the random variable at the nth time step is 0. N plus 1th time step is 1. That is P0. This is a state. The red color thing, this is a state. This is a time. So please note down that thing, state and time. These two. That's how that thing, that's a notation only. The conceptually you all understood. I know that. This notation, please follow the notation here. State, time. That is P01. This is 0.7. P10. This is if you write this is 1, you can also say this is 0, 1, 0, 1. All the values, P11. That's how they're just a notation. This is a stochastic matrix. These are all transition probabilities. These are known as the transition probabilities. These are the states, and the entire thing is called stochastic. I mean, the transition matrix, and this is also a stochastic matrix because row sums are 1. Okay. Please make sure that these foundations are very much clear to you, because this is the rest of the course. As we are passed through the foundations, you see that these are again as this gets more and more advanced. And when you are clear all the basics, the advanced things also looks much easier. Okay, let's go to the next example. We will compute p square. So let us check for p square. We all know that matrix multiplication p into p. So if you compute yourself, I just computed, and to save the time, you can also verify yourself. So p square. So p square, if you see that again, P into P, the P is a transition matrix. P square also again, row sums are 1. Both. So P square also stochastic matrix because the row sums are 1. So P square also, you see the probability again, 0. P square, this part, if you consider P square itself as one new transition matrix. These are again, you can write down as various values. P00, this is P00, P01, that means P square. If you consider these itself a new matrix, this just becomes a new P. P00, P01, P10, P11. You can compute yourself. I'm leaving that as an exercise, so you can verify. So that means everything you can. Similarly, P cube. Just to save the time, I'm just leaving. So if P is a stochastic matrix, this is a point to be noted. If P is a stochastic matrix, then P square also stochastic matrix, P cube also stochastic matrix, and so on. And P power n for all n is also stochastic matrix. So we learn the notation Pij, and using the notation Pij, we also defined what is the stochastic matrix. I mean, the transition matrix is a stochastic matrix only if row sums are 1 for each row, or if the column sums are 1 for each column. If the both row sums are equal to 1, column sums are equal to 1, we say it is a doubly stochastic. But just for simple regular stochastic matrix, if a row sums are equal to 1, that's enough, or a column sums are equal to 1, either one is enough. Because we can if you make a transpose of the matrix, that means it is a column sums will be equal to 1.
So I have a query here.
Yes, please.
So what could be the meaning of P square Ij? So is this the probability of making a transition from the state I to the state J with one state in between, or what?
2 steps.
So from the state I would be making transition to which state, and then from
somewhere, but again coming back to 0. Let me go to the P square. Here you see the P square. Let me just take 1 minute. It is a typo here also again. This is yeah. You see here P square 0.23, 0.77, 0.22. So if you consider this itself as a new matrix, this is a one-step transition. Someone, I think, need to be muted. A lot of resound I'm getting.
It's Viswa Prakash Jha, mic is on.
Okay. So if you consider P square itself a single matrix, this is a one-step transition.
Yes, because the properties of the stochastic matrix are being followed here. It's true.
Yes.
But then what is the meaning of this P squared 0, 0? Making probability of making a transition from the state 0 to itself by going through which? I mean, what could be the meaning of the square here then?
Yeah, this 0 to 0.
Yes.
So 0 to somewhere, one step. From there to 0, it's 2 steps.
So what that somewhere is?
It could be any other state. That means since it is 0 to 0, it could remain 0, 0, 0, 0, 0 to 0, and 0 to 0, or 0 to 1, 1 to 0.
Let us take the example of this P squared 0, 1. So a possibility could be from 0 to itself and then from 0 to 1. The other could be from 0 to 1 and then from 1 to itself.
1 to itself, yes.
Does it mean like this only?
Yes. Only because this matrix has only 2 states. Either it can be from same to same or same to another and come back to the same state.
All right. So it seems similar to the transitive closure then. Fine, sir.
Yeah, same property.
Yeah. Thank you, sir.
Yeah, good. It's a good question. So meaning of P square means higher order. When you go to higher order, it will transit to some other state and come back or remain there. Similarly, if you take the transpose of the matrix, the initial values, initially you see that 0.3, 0.7, now I took the transpose of that, and that is also stochastic matrix because the column sums are 1. Similarly, PT, the transpose PT square, PT cube, and so on, they are all stochastic. So these all you can verify yourself take it as a homework to check yourself. PT, and then after the lecture you can in the home you can verify these things. Similarly, let us take example of a doubly stochastic. Q is another matrix with 3 by 3. Again, you see this row sums and column sums for each row and each column. This is 1. 0.3, 0.4, 0.3, 0.3, 0.5, and 0.6. The sums are 1. This is 1, 1, 1. The sums are 1. So this is a doubly stochastic matrix. Okay. So with 3 examples, I'm going to the new another concept I'm going to start. So if you all of you are clear, I can revise quickly, and then if there are no questions, I can move to the next phase of the training.
And what this
of course, we'll come back to the transition matrix. Keep on coming back at various stages. But this particular part, understanding the notation and that doubly stochastic transition matrix. If you have any question, I can just hold for a minute, and otherwise I'll move to the next stage.
So what this doubly here is in the doubly stochastic matrix?
For doubly stochastic means the rows are, some of the rows also equal to 1 for each row. Some of the columns also equal to 1.
Okay. All right.
Yes, that's each row. If each row equal to 1, it's a stochastic matrix. Each column equal to 1 stochastic matrix. But when each column sum is also 1, see that here 0.3, 0.5, 0.2, the sum is 1.
Yes.
Here 0.4, 0.2, 0. Sum is 1. Sum is 1. But row also, sum of each row also 1. Yes. So this is both sides is a doubly stochastic. Double means both sides. Double stochastic, or they call it doubly stochastic.
Right.
Good evening, sir.
Yes.
Sir, can you explain it with the help of example of blood pressure or this temperature? This P square.
A P square, okay. You mean this one, this example?
So
yeah. Let us suppose say 0, 2 states are there. Suppose normal blood pressure. 0 stands for normal blood pressure. 1 stands for, you just note some symbol. So suppose doctors give a notation for a patient, on the patient report. 0 stands for say normal blood pressure, and 1 stands for high blood pressure. Suppose say 2 states are there for a patient. The patient enters the clinic. The patient on the patient report card, doctor puts some notation, and then each time the patient visits. This is a good question. I want to. So how do we use it for a practical purposes? Then each time patient visits, normal blood pressure, and then again doctor visits after say 24 hours. Whether the patient remain at the normal blood pressure P00, or patient becomes higher blood pressure during observation. So that way you can consider 0 as a normal blood pressure, the state notation. So 0, 1 is our choice, or you can put normal, N, and our choice. These we can change it into normal blood pressure or high blood pressure. Normal high. So 0.3, 0.7. So transition, patient is transition from normal to normal. Given the patient is normal, probability of becoming high. So P, probability of high blood pressure, given it is a patient is normal, is 0.3. Similarly,
it should be 0.7, no, then?
Yeah. And then Sorry, this is 0. Thank you. 0.7. Given H, already high blood pressure, remaining in the high is 0.8. Like that, all the 4 cases. So these notation, this thing is the modeler need to introduce. But the doctor would only tell that normal blood pressure. Then the probability of computing what is the chance that a given patient who admits into the hospital remains normal, the COVID patient, out of anxiety. COVID patients have a lot of anxiety and other things. So they admitted in the hospital, normal blood pressure, COVID, and due to anxiety, they become a high blood pressure. Or high blood pressure after treatment might become normal. So this how to compute that, these values, that's we'll again see later. Computation of the,
Excuse me,
sorry, please go ahead.
yeah. Sir, can you explain on same lines what is the significance of P square?
P square?
Yeah, like normal high blood pressure. Two stages are there, but in
Two
the
stage,
case,
yeah.
yeah.
Two stage, what happens now here? Suppose the same thing here, the 0.23, 0.77. Now let us take this matrix, two stage. So 0.23, 0.77, 0.22, 0.78. This is another matrix. Say this is a P square. P square is our say new P. Say let us call this Q. Or let us keep it P square itself. Now P00 stand means it took 2 days or 2 observations. Let us consider that each day doctor sees the patient. Say first day, that means probability the first time the whatever value here, let us say x0 equal to normal blood pressure. Then x1, somewhere we don't know x1 because this information this particular matrix doesn't tell us what was the value of x1. Only it tells us after second step, at the second step, that means x2. Is equal to 0. That means normal. That for such probability is 0.23. If you treat this as only one single transition matrix without two steps, then it becomes x0 to x1. If you treat this as a P square, this becomes x0 to x2. And x1 we don't know. X1 could be, so if there are two, that means 3 states are there. Let me write the diagram here. We'll also learn how to draw diagrams, normal blood pressure and high blood pressure. 2 states. So normal to high, high to normal. Normal to high, the probability is, in one step, probability is 0.3. And high to normal 0.2. The probability to return back from high, this is high, to normal. Now, normal blood pressure to high and high to again normal to come back, this is 0.23, or normal remaining in normal could be 0.23. So at second step, Second day, first day, COVID patient admitted. Second day, doctor again tested the pressure, normal. Third day, when admitted, if you call X0, admitted today X0, first day X1, second day X2, X2 again came back. But second day reading is not not provided for us in this example. In second time the patient has come back. So that's how one has to read. As we see that more examples, we will provide more data. Then you will see that each state how to come back, like a higher standard, like a 3-step transitions when we see.
Sir,
Okay. Yeah.
sir, the below one, it has to be, it is 0.22, sir. From high to
0.22,
normal.
Yeah, 0 यहाँ लिखा है ना, वही लिखा है उधर 0.22.
It's looking at 0.23, so that's why I asked, sir. Okay, sir.
Yeah, 22. Thank you.
Thank you, sir.
Good. अभी clear है ना, everyone?
Right.
Those
Ji,
who
sir.
are- Good, very good.
Right, sir.
So we'll go to the next. Yeah, it is important. That spending time on the what we discussed is an important aspect, because this is called foundations. Those things, the notation part, the meaning part. So you are all asking very sensible questions. The foundations, one has to be clear, and I'm happy for that. Next, let us understand counting process. Again, we'll come to those matrices. We won't leave them, because stochastic process is about the transition matrices. Let us see a counting process. Counting process, the name itself suggests it's something we are counting, like number of cars at a signal, number of particular cars. We don't know, or number of certain branded cars, or number of buses, or number of trains, anything. You are counting it. Or in a cricket match, number of sixes, frequency of number of sixers or number of wickets, something which you don't know prior. There is no pattern. Randomly the events are occurring. That kind of things you are counting. So a counting process, I'm reading the counting process is also stochastic process with the discrete time steps. That means you are observing first over how many sixes, second over how many sixes, third over how many sixes. So something you are counting. So first over is a first time step, second over second time step, third over third time step, according to your own definition. I mean, our choice. Or first 1 hour, how many cars crossed certain signal junction. Second hour, third hour, how many cars. So you're counting. And random variable is xn, stands for number of cars at nth time step. So this is called counting process. So collection of, when you start counting, you're standing, the number of, suppose number of sixers in a match, xn stands for number of xn. This stands for, suppose, a number of sixers in nth over in a cricket match, in a, say, one day, in a T20 match. So 20 overs are there. So x0, x1, x2, x20. Then that's a counting. So x1 means first over how many sixers? It could be 0. It could be 0. Second over, it could be 1 6 or 2 6, a number of sixers. Whatever you're counting, whatever the definition of the random variable. Random variable, how to define is your choice. So that it's called a counting process. Then state space could be any number, collection of number. It could be, suppose, no sixers in a match, 0. Or it could be 1 sixers and so on. So 20 in a cricket match, that naturally there are each ball, if they hit 26, so in a over 6 sixers. So in a match, maximum number of sixers is 120. T20 match, 20 over match. So your state space is, in that case, cricket example I gave, state space is number of sixers. It starts from 0 to 120, the state space. So counting process also a stochastic process. The idea is, this is number, when you start counting number of sixers, it's a non-decreasing. That means these numbers either remain same. Suppose first over somebody hits 6 and the rest of the match no 6. So total number of sixes end of the match is still 6. That's called non-decreasing. अगर ज़्यादा हो सकता है लेकिन first over somebody hit 6, it remains same, or could be more numbers. That's what meaning of non-decreasing. So if it is a discrete example, a continuous example, we just write instead of xn, we write xt, just a notation. The idea is also same. The time steps are continuous. Like car example, within an interval. In the cricket example, that's a discrete example. Car example is a continuous example, continuous, like blood pressure, all these things. So let us understand the theory of counting process. So for simplicity, let us understand, let nt be the number of events up to time t. आप ध्यान से थोड़ा follow कीजिए इधर. Notation क्या हो रहा है? No, nt be the number of events, number of sixers, whatever. Let nt be the number of events up to time t. This nt called counting process satisfies 3 conditions. N0 equal to 0, obviously at the beginning of the match not started, number of sixers is 0. Or counting not started at the beginning, no cars, 0. And nt is greater than or equal to 0 for t positive. उसके बाद भी then if there are no sixers, it could remain 0 or more than 0 as t increases. So nt greater than or equal to nt1 for t greater than t1. That means number of events at a later time point, number of such events is greater than or equal to the number of events at a previous time point. हाँ बस notation और कुछ नहीं इधर. 3 things. N0 equal to 0, nt greater than or equal to 0, or nt greater than or equal to nt1 for t greater than t1. Three conditions. And the fourth condition is the number of the difference between nt and nt minus 1 gives the number of events during the time interval. Like if the first over, suppose up to end of the first over, there are 5 sixers or somebody hits in the match, and then end of 13th over, there are 13 sixers are hit. Then the difference between the 13th over minus first over, then the difference of number of sixers. That's what it means. So difference between the two random variables. This is a random variable. This event, this difference gives the number of events during the time interval, first over to 13th over. Example. So the number of so this is how the counting process is defined, and we'll see that counting process is a Poisson process. थोड़ा theory इधर है, and then we'll easily sail through. Sorry. So a Poisson process is defined as lambda with the parameter lambda t, parameter lambda t here. If P and T stands for Poisson process with the parameter lambda t, it is event rate. P and T be the probability that there are at time t n events occur. The notation here, P and T is defined as probability that there are n events. This suffix events time. P and T stands for suffix and time. अब उसको थोड़ा, that means number of, in notation में लिखा इधर number equal to this is a number, this is a time. Here T stands for time, N stands for number. So we know that we all know, recollect from your undergrad days or master's days, e power minus lambda t power n by n factorial. This is the Poisson mass function for with the parameter lambda t, e power minus lambda t to the power of n by n factorial. So we'll show that the counting process is a Poisson process, and then we will use the generating function which we defined yesterday. I mentioned yesterday that generating functions are important. We'll see that generating functions are used here. So feel free to stop me anywhere it is not clear. So we'll know that we already discussed n0 equal to 0 and t greater than or equal to for t greater than 0. And probability of occurrence of one event during a small interval, we assume that there are 3 assumptions are there. A, B, C. So A stands here, first assumption, probability of occurrence of one event during a small interval 0 to H. So let me here do one thing. Let me draw a line which I should have drawn in the previous slide. तो इवेंट हम लोग यहाँ डिफाइन करेंगे, टाइम कैसा क्या हो रहा है. So this is how, this is starting time point 0. Here, just for your visualization, this is n of t1. Number at time t2 and so on. Yeah. So number of event, this is at n0. N of 0 is 0. Initially no sixers or initially no cars, and then after some time nt1. So nt1, if there are still no sixers, nt1 still be 0, or nt1 is more than 0. That's why greater than or equal to 0. And nt2 similarly is greater than, still no sixers up to time t2. From the beginning still it is 0 or more than 0. That's why nt2, n of t2 number, it could be greater than nt1 or equal to nt1, greater than or equal to nt1, nt2, and so on. That's a counting, anything you're counting. So three assumptions here. So initially 0, that's what the three assumptions discussed in it later, and then difference between nt1, nt2 minus nt1 gives us the difference. Now here, small interval. So let us understand the three assumptions, and again I will draw another figure there. So probability of occurrence of one event during a small interval we define as lambda times h plus OH, order of h. So lambda is, that means small event occurring in a small interval 0 to h. H is an interval. 0 to h is a time. This is the interval. And probability of occurrence, no event is 1 minus lambda h. So occurrence, non-occurrence, all of you know that in a probability of getting a heads, ph, then probability of getting tail is 1 minus ph, because only two events are there. If one event of occurring something is lambda h, not occurring is 1 minus lambda h. That's it. And probability of occurrence of more than one event is ignored, is 0. More than one event. See here, more than one event. More than one event is ignored. So in sum, again, in the beginning there are 0. Probability of occurrence of one event in a small interval is lambda h. Probability of no event is 1 minus lambda h. So one event lambda h, no event 1 minus lambda h. More than one event is 0, order of h. That is negligible. In the interval, this is the interval. So यहाँ से begin हुआ. So if you begin the experiment, counting from here, some time here.
Is this 0 or is this small o?
Small order of h is negligible. That means the order of h. That is a.
Okay, all right. Small o order of h.
Yeah.
All right.
That be negligible, which I call 0.
Yes.
Sir, we also have to define what is small interval when we start.
Yeah, this h 0 to h is our choice. H is some interval. H for positive. H is greater than 0. Any h which is greater than 0.
Okay.
0 ke baad, anything. It could be here. It could be here. Is that clear? H.
Yes, sir.
Good.
So what could be the other event in case of number of sixes? We are counting just the number of sixes and no other event.
Correct. Only sixes means only one six occurrence of 1 6 is lambda times h if the interval h is the interval, suppose, good question. H is the what did I say here? H probability occurrence of during a small interval. I said 0 to h. H could be say 5 hours. If it is a 5 hours, 0 to 5, that interval, 5 hour interval.
I'm asking
Then
about
lambda times 5 lambda. Sorry.
Excuse me, sir. I'm asking about more than one event during a small interval. One
As
event.
more than that is a negligible.
What could be
Order
the
of
other
h.
event?
More than one event is order of h. That means either event, if you define event, one event as a 1 sixer, so more than 1 sixer is ignored. If the event is 10 sixers is one event, more than 10 or 10 sixers are ignored.
Okay.
The way you want to define an event. Good. These kind of critical thinking is needed, as you all asking very sensible. I mean, very much right, very relevant questions. So this is how we define three assumptions, three properties, whatever you say. And then this is third point is that property is that during this interval, the events during this interval are independent of the prior events. T1 to T. अब यहाँ suppose this is your T1, and somewhere here you have T. So number of sixers in this interval, whatever done already, they are not influencing the number of sixers here. That's what it means. Number of events during T1 to T, this interval T1 to T, are independent of the number of events of this interval. अब किसी सिग्नल पे खड़ा हो जाओ and then number of cars, certain cars, number of cars in first 1 hour are independent of the number of cars of the next 1 hour. Number of cars of certain brand you want to count. So that is that means that is assumption here. So these three have to satisfy. First lambda h, then the no event 1 minus lambda h, and then more than one event order of h, negligible, and then the number of events during this interval are independent of n0 and t1. So a number of intervals independent of that means n0 stands for number of events at 0, number of event t1, number of and so on, blah blah, number of t1, and then these are all the events during this interval are independent of these previous events. Yeah. The proof, let us see the proof. So three properties, the meaning, let us understand again, the same thing what we discussed previous slide in terms of the notation I'm writing. So if you see that, if there are R events occurred, that means at time T, there are R events occurred. Again, notation. You all understood what I'm saying, but there's just notation. R events occurred at time T plus H. That means T to T plus H, matlab kya, the interval is 0 to H. 0 to H, in general, we write T to T plus H. One event, R to R plus 1. So here, what is R? Number of events. In terms of the state space, R is what? What is R?
State.
Very good. It's a state. R is a state. Good. And T is a time. So state is moving R to R plus 1. In how many steps? How many, what in the steps means here time interval, T to T plus H. In the 0 to H in time interval, in that interval, one event occurred. So uska probability hai lambda H plus order of H. That's what hum log previous slides we just saw. Just same thing what we learned in terms of the language, we are writing in terms of notation. So second property says that here you see the state R to R remaining same. That means no event occurred. Up to time T, R events, T plus H also R events. That means no more events occurred. That means no events occurred. No events means 1 minus lambda H. 3 or r plus 1. More, so greater than r plus 1. Either r, so more than one event. More than one event occurred, order of h. That previous slide, whatever you just learned, we saw the same thing in terms of the notation. So the thing what we want to do is we want to compute the P and T. Our aim is to what?
Excuse me,
Just to
sir,
recap our aim. Ask.
Sir, is it possible to go from R to R minus 1 state?
R to R minus 1 is not defined here.
Okay.
Because counting process, एक बार sixer of cricket, imagine cricket match, once you hit the 6, once the first over somebody in the match 6, you cannot delete the 6 again. That is already counted. So up to 3 overs, there are 2 sixes are there in the match. Again, 5th over also, at least 2 or more than 2. There cannot be 1 6. Because you are counting, that's what the counting process. You either count remain the same or count increases. Number of cars remain same, number of car increases.
But sir,
so here what is that we are doing?
That can be possible in birth death process, I think.
Correct. Or when we learn that will happen. Correct. So here, sorry, you have any question?
In medical, a temperature can go from high to low or low to high, then it will decrease from R to R minus 1 state.
That example do not fit here because we are not counting anything there.
Okay, sir.
Even here, counting of events, some events, that kind of things, we bring it here.
Okay,
like,
clear, sir.
Clear. Some events of occurring like, say, number of patients, number of COVID patients with, say, COPD, or number of COVID patients with hypertension. That's a count. And you are counting something. Wherever you are counting something, this example is for that kind of problems, where you are having, so when every day you are hospital admitting COVID patients, and then that COVID patients, you are counting how many COVID patients are coming who have hypertension.
Okay, sir.
A number of COVID patients who have blood pressure, number of COVID patients who have diabetes, number of COVID patients who have nothing. That's suppose you are counting that. So this example is for that kind of questions. You are counting certain things, that event is a count here. Okay. Now, what is that we are trying to do here is, as initial notation I mentioned, we are trying to, our aim is here in this question is how to obtain P and T. That means what is the probability of getting N, size N of number of some events, say by end of the day, probability of getting N COVID patients who have hypertension by end of the day. P and T, probability. What is the probability that by end of the day or by end of the season, probability of getting so many COVID patients with hypertension? You are counting. So that kind of problems we have to tackle through counting process problems. So I'll just finish up this slide and I will take a break. And then during the break, you can recap what happened. So the idea is here, P and, since you are all active, this notation you can follow here. P and T plus H stands for what? Probability that there are N events up to time T plus H. Because here I defined, P and T plus H equal to probability that there are N events up to time T plus H. And T plus H stands for number of events up to time t plus h. And this is notation. Number of the, so this stands for p and t plus h stands for the same thing, p and t. P and t is up to time t, t plus h. P and t plus h stands for probability that there are number of events up to time t plus h is equal to n. Number of COVID patients with hypertension equal to n, end of the day. So this can be expressed as, this one step you all carefully follow. Probability that there are n patients at t and time t plus h equal to probability that there are n events up to time t and
No
no
occurrence.
event. 1 minus lambda h plus order of h means no event. This is no event. Or plus means or. We discussed yesterday in the review of probability. An event A or event B, probability of A union B is equal to probability of A plus probability of B. Total events. So probability of total law of probability also we learned yesterday. We're using that. So probability that there are n events up to time t equal to probability of n events up to time t plus h. तो यहाँ इंटरवल ला लीजिए यार 0. This is t. This is h, somewhere say h, t plus h. This is 0. So 0 to t, n events, and t to t plus h, how many events? No events, because you are trying to get have n events up to time t plus h. Or if there are n minus 1 here, how many events occurred here? 1 event.
1.
Because total it should be n events. Total n events up to time t plus h. So n events, यहाँ तक n events, that means if they are in a match, suppose in a match, if there are, in the beginning there are 0 sixers, in the say 10th over, if there are 5 sixers already occurred, 5 sixers somebody hits in a match, and then 11th over, it could be 1 sixer, or it could be or 0. So by if you want to compute number of say instead of here 5, you put it here. Total you want to have 5 sixers by end of 11 overs. So by end of 10, already 5 sixers somebody hits in a match. You have a chance of getting only 0 sixers, or if there are 4 sixers by the end of 10 overs, there will be 1. Because end of the 11 overs, you want to have 5 sixers. The probability or that kind of probability you are computing. So probability P n t plus h is equal to P n t. That means number of the size n, number of count n, and no event, or n minus 1 and 1 event. So you simplify that equation, P n t multiplied by 1 and P n t multiplied by minus lambda h. P n t in order, this is ignored. P n minus 1 lambda h, P n minus 1 lambda h, and order of h. So all together we can write 1 order of h, that's enough. So all terms are here. And then this, please verify in your home when you are there, even though I'm showing the slides are shared with you. Still, please practice yourself, and if there are any doubts, bring back either during the break and next lecture, or even tomorrow, next day. So don't leave anything because this, as we mentioned, the training is for you all. This is a good opportunity for you to practice completely theory also, examples also in the home. Come back with any questions next day. So verify that P and T multiplied by 1, that you bring it on the left side. So that's P and T minus lambda H minus lambda H P and T. Similarly, Pn minus 1 lambda H, Pn minus 1 lambda H, and order pura order idhar chala gaya. Then you divide this Pn, this the left hand side part, this part you divide this by H and taking the limit. So divide this by H, Pn T plus H minus Pn T by H, and take the limit as H tends to 0. This becomes a limit as Pn T and H goes to 0. See this part. So take a limit, and right hand side, if you divide by H, you get this H gets cancelled, H gets cancelled. That means minus lambda P and T, H gets cancelled, minus. So, but left hand side becomes P n dash T. This is a definition of the derivative. Derivative definition. So this becomes d by dt of P and T, d by dt of P and T minus lambda P and T plus lambda Pn minus 1 T order of H. So this becomes a differential equation. I'll stop that here. I'll stop this part of the lecture here. And then continue after the break. So I'll leave the slide as it is here.
Sir, I think order of H will not come because H approaches to 0.
Yes. So when H goes to 0, this will be ignored next step.
Yes.
Yes, you're right. So because order of H is defined as order of H, when you divide by H, as H goes to 0, we'll ignore that. You're right. Thank you.
Excuse me, sir.
Yeah.
In the equation 1, one term should also be there for the occurrence of more than one event times order of H.
More than one event, ignore ho gaya. That's why we don't have to, because you can write one more. All together becomes this order of H. We don't have to write many orders of H.
Yes, but we must mention order of H one time at least.
One time here, this one H includes all.
Okay.
You mean where to mention the order of H? I didn't understand. You mean you want to write here 2 times?
In the equation 1, I want to say.
Oh, equation 1. See, there is no such probability. More than one event kaha? Because up to n, P n T plus H means n events up to T plus H.
Yes.
N events n minus 1. Then there is no third option. N and 0, n minus 1 and 1. N minus 2 ka chance hi nahi. N minus 2 chance is not there anyway, you see.
I think order of P, this term must be included, plus Pn minus 2T times order of H, which will be negligible for the small h.
They are all, yeah, n minus 2, n minus 3, n minus 4, all more than one event in this are not counted, you see. In this interval, more than one.
I think, sir, because H is a very, very small interval approaches to 0. So this implies there will happen only one event. And it is not possible to happen another event also.
Correct. That's what I'm telling you. More than one event is ignored. More than one is the possibility of occurrence of more than one event is negligible. That's it. More than one event we don't have to consider here. More than one event, there is no possibility of occurrence of more than one event. For definition, our assumptions here, more than one event is order of H.
Order of H. That's why I was mentioning that for small h, that will be surely 0, but there are chances order of H.
Yes, order of H. So order of H means it is not counted. There is no chance. The R of H means is not the smaller probability. You don't treat OH is not doesn't mean that probability. Small probability is different than ignorance. We are ignoring that particular event. We're not saying a small probability to happen. No, we are ignoring the event. And then we'll be back.